So Assalamu alaikum and warm greetings from my side to all of you. I hope you all are good and are staying safe in your homes. So today's lecture will be a kind of extension of the previous topic, and then I'll take you to some other new concepts. But I guess it's important to mention some of the concepts which we have not, which are based upon the band shapes, right? So in the previous lecture we did the Kronig-Penney model. This Kronig-Penney model is used to explain the band formation, right? And how does it explain the band formation? You know that there are a series of allowed bands separated by, that is, we have series of allowed bands separated by the forbidden gap, and this solution exists for an electron moving in a crystal, isn't it? Another thing was that you have the bands, but there are no forbidden gaps, and that is for the electron when it is free. That is the case of a free electron, right? So let me select the black color. Yeah. So now let me draw again the bands. You know, the bands are like this. Okay. Let me try to draw it symmetrically. Let us say that this is the first Brillouin zone. We know we'll use the reduced K-space diagram, right? Where all the bands are confined to the first Brillouin zone. That is the reduced K-space diagram, right? As I already told you. So the first allowed band is like this. Then the second allowed band is like this. The third is somewhat like this, and so on. So this is for k equals to 0, this is for k equals to pi upon a, and this is for k equals to minus pi upon a. Alright, and this hole is in the first Brillouin zone. So it is the first allowed band. This is the second allowed band. This is the third allowed band, and it continues like this. And let me not forget to write the vertical axis, which is E, that is the energy axis, right? So the energy is increasing, right? Okay. Yeah. Now see, based upon these band shapes, we can have the direct and indirect band gap semiconductors. Okay, now you'll ask me rather that how. So when these E versus K have been visualized in various semiconductors, say for example, it's just E. Let this be E and this is like K. So you have the lower, this is K equals to 0. So let us say this is the valence band, and the top energy will be EV, right? Now, in many of the semiconductors, the pattern of the allowed bands is not actually uniform. That means the maximum of the lower band does not coincide with the minimum of the upper band. What do I mean by that is somewhat like this. See, this is the bottom of another band, that is a higher band, and the lowest energy is EC, right? Where we have along this axis the varying energy E, and this is your K. Alright, now this point is the top of valence band, and this point is the bottom of the conduction band. Based upon their orientation with each other, these semiconductors are classified further as direct and indirect band gap semiconductors. Fine. When the maximum of the valence band lies just below the minimum of the conduction band, it's known as a direct band gap semiconductor, and where it does not, it's known as an indirect band gap semiconductor. So I'll just show you how can it look like. Say for example, the bands in the gallium arsenide have been visualized like this. So this is the band gap EG, okay, in case of the gallium arsenide, okay, and it has further some other values as well. So I'll not talk about it at this time, but here you can see that the maximum of the lower band coincides with the minimum of the upper band, and so that is why it's a direct semiconductor. So gallium arsenide is a direct semiconductor, right? So the electrons, if they are in the bottom of the conduction band, they just have to make a direct jump so as to reach to the valence band, right? Okay, so it's a direct. Now, what is an indirect? An indirect, it's like this. See, the bands which are observed, right, the bands which are observed in silicon, these are again E versus K, E energy versus K. Okay, now see the difference. This thing is the top of the valence band and this thing is the bottom of the conduction band. So the band gap difference is this thing, because you can measure band gap difference only between the top of the valence band and the bottom of the conduction band, right? So here this means that the bottom of the conduction band is not exactly perpendicular to the top of the valence band. It is somewhat deviated. Such a kind of a semiconductor is known as an indirect semiconductor. So to our surprise, the mostly used silicon and the germanium both are the indirect semiconductors. And in case of the indirect semiconductor, electron which is at the bottom of the conduction band, if it has to make a transition from the conduction band into the valence band, I mean if it has to make a jump from for the recombination from the the conduction band to the valence band, it cannot make it directly like this. It first has to go to this place so that it loses some of the momentum. And then it makes a transition to the top of the valence band. This thing occurs so that the crystal momentum is conserved. Okay, that is the law of conservation of momentum. Alright, so these are the direct and the indirect. So your band shapes are also responsible for classifying semiconductors into the direct and the indirect semiconductors. Now based upon this concept only, I'll tell you another important feature which is the positive and negative effective mass. Now you'll ask me, what is this positive and effective mass? Because we've just heard about the effective mass. So effective mass is what? It takes into account the quantum effect, that is the internal forces, whereas the simply your rest mass is simply where you do not have any internal forces. Okay, so now what is this positive and negative effective mass? In my previous lecture where I told you about that was probably my first lecture where I told you about the concept of electron and hole, right? We had written some of the equations by taking the bands into account. All right. Yeah. Now see, see. What we'll do is, we have a band here like this. We have a band lower like this. The top energy of this band is EV, the bottom energy of this band is EC, and the energy goes on increasing like this. That means in this band, that is the top band, energy is greater than EC, and here in this band, EV is the highest energy, and the energies, all of the energies in this band are below EV. That means EV is greater than EC here, and both of these shapes are those of a parabola. So we can write separate equations for two, just as we did in the previous lecture. Alright, just as we did in the previous lecture. And what we can write is E minus EC equals to C1 K square. Okay, and the another one, E minus EV equals to minus C2 into K square. Now why did we write this? We wrote this because this is the equation of a parabola. I'm just repeating it here again. So this is equation of a parabola. Okay, this is opening in the positive y direction, right? Now this thing is again the equation of a parabola, but it is opening in the negative y direction. That is why the sign negative is here. Okay, just to make it clear to you, maybe some of us are not so good in mathematics. So it is negative sign is, that is the reason we have the negative sign. And then when we differentiate it and when we differentiate it and that is when we do d square E divided by dk square for both the equations, we'll get, for first equation we'll get twice C1, right? Yeah. And for the second equation we'll get d square E upon dk square as minus 2C2, right? Now we know, let me just draw a line over here. We know that 1 upon h cross square d square E upon dk square is equivalent to 1 upon m star, where your m star is the effective mass. So now you have this thing. So from here we can write 2C1 upon h cross square equals to 1 upon m star, and here we can write 2C2 minus 2C2 upon h cross square equals to 1 upon m star. Okay, now why did this C2 come out to be negative? If C2 was negative here, then this equation would have become positive. But see, E minus EV, okay, E minus EV, you can say that your EV is greater than E. Alright, so EV is greater than E, so C2 has to remain a positive quantity because the difference of these two energies is a negative, so you cannot change the sign over here. So that is what is happening. I hope you are able to understand me, what I am trying to tell you. If in case you have still a confusion, you can anytime write back to me or just mention in the comment section. Alright, So, and we are soon going to have another interactive Zoom session. Okay, now if we take the first case where 1 upon m star equals to 2c1 upon h cross square, it implies our m star will be the reciprocal of 2c1 upon h cross square. And second case is where 1 upon m star equals to 2c2 but negative upon h cross square. So it implies m star, m star equals to 1 upon minus 2c2 upon h cross square. So this is what is the positive effective mass, and this is what is the negative effective mass. So where does this negative and positive effective mass exist? The positive effective mass so the electron in top band has positive effective mass, and electron in lower band or the bottom band has a negative effective mass. All right, yeah. Okay. Now let us extend the density of states to the semiconductors, right? Okay. Now you all know that density of states, which is given by G of E, is equivalent to, because we have already derived it in the class, it's 4 pi into 2m, that is m is the mass of the electron, 3 by 2 upon h square, sorry, it's h cube, it's h cube under root of E. Okay. Now we've now studied the EK relationship and we have understood the EK diagrams look like a parabola. So the parabolic relationship between the energy and the momentum of a free electron is energy equals to h cross square k square upon 2m, right? This is the energy of a free electron. All right. Now, if this electron is in the bottom of the conduction band, so what are we going to write? If this electron exists in the, if the same electron, you know, if your same electron is in bottom of conduction band, so how will we modify this equation? We'll write E minus EC equals to h cross square k square upon 2m. So that means now the energy which was previously root of E will automatically become E minus EC, so that we may write G of E as 4 pi 2m. Now it will be 2m star, because now the electron is in the crystal and the free electron mass or the rest mass is replaced by the effective mass, 3 by 2 upon h cube under root of E minus EC. Okay. Similarly, using the same methodology, we can write the energy, and we'll simply place a subscript C over here. That means the density of states in the conduction band. Now we will write density of states in the valence band. It will be 4 pi 2, and this thing will be mn, because it will be the rest mass of the electron, right? And now it will be twice, it will be mp star upon h cube to the power 3 by 2 EV minus E. Alright, because then only it will be positive. So here what we'll do is we'll write this as, this is M, this will be written as Mn star. Okay, because valence band, you know that there is the moment of the holes. Now let us see. This is a constant, this whole term is a constant. So if we have to interpret the relationship between the energy and the density of the states, it is Gc of E is proportional to the root of E minus Ec. So that means as the energy goes on increasing above the conduction band energy, the bottom of the conduction band, the density of states increases as a square. That is simply E minus Ec is proportional to Gc of E whole square, isn't it? And same is the case with the valence band. In the valence band, it is EV minus E proportional to GVE square, right? So that means as the energy goes below the top of the valence band, the density of states in the valence band increases. Now can we just picturize it if we try to draw it graphically? Yes, we can. And how do we do it? Let's just take a look. Okay, Alright, this is already given in your book as well. I would like you to have the reference of the page numbers 63 and 64. Alright, of the Donnell-Lineman, right? Now let us say we take energy as the vertical axis, right? And this is our EC and this is our EV, and this thing is your energy increasing like this. Okay, this whole is the energy. Right, now we're going to plot this. Okay, let me draw a line for the conduction band. Let me draw a line for the valence band. This means that we have to plot GC, that is the density of states versus the energy. So it will look like this, and here it will look like this. Okay, so this will be your GC of E, and this will be your GV of E. And remember, these two will be symmetrical.